everyone. This video is me going over the pedigree notes. So a pedigree will show you how a certain trait will go through different generations. We've got 3 generations here. P generation is the parents. F1 generation is the sons or daughters, and the F2 generation would be the grandkids. So the only person who married into this family is actually this guy right here, because this is the daughter of these two, but he married her and had these kids. So it's like a family tree, and it's going to use symbols like the circle for females and the squares for males to trace traits through generations. So we can go through many generations and show how these traits what pattern of inheritance they will show. So maybe it's dominant, maybe it's recessive, maybe it's something else. So it can show how traits like even diseases can be passed through a family, and by analyzing the pedigree, we can kind of figure out, is it dominant or is it recessive? Now, this one we're going to go ahead and give you some information. Brown hair is dominant, blonde hair is recessive. We're going to trace blonde hair, and these two parents, this one's heterozygous, he's got brown hair, and she is homozygous recessive since she has blonde hair. So again, circles are females, squares are males. Each row is going to be a generation. Now, dominant traits will rarely skip a generation. They're usually going to be found somewhere in the generation, but recessive traits will often skip generations. Remember, they can be hidden. These two parents right here, they didn't have a trait, but their kid did, so it skipped them and went to them. So we can see the phenotypes, who has blonde hair, who has brown hair, but the genotypes we're going to have to figure out. So that's usually what this ends up being. So if you have a dominant trait, people with brown hair, they could be homozygous dominant with 2 capital Bs, or they could be heterozygous with 1 capital B. So we don't know which one they are based off of just whether it's shaded or not. We have to figure it out based on what everybody else has. When someone has a recessive trait, the only thing they can be is homozygous recessive, because that's the only way that you'll show a recessive phenotype, is to have 2 of the recessive alleles. So to figure everybody out, when we got to label our genotypes. And the easiest thing to do first is to start with the recessive people, because we know the only thing they can be is homozygous recessive. So we already had her filled in, 2 lowercase b's. Everybody else who's blonde is also going to have lowercase b's. The second step, since everybody else is dominant, we know for sure they have at least 1 dominant allele. Now, maybe they have 2, maybe they have only 1 with the recessive second allele, but we know they have at least 1. Now, the third step, once you've got everybody's first allele, you got to look at the parents and the kids of who you do know. So this daughter right here, she had to get her capital dominant brown hair allele from her dad. He's the only one who could give it to her. Now, did she get both of those alleles from dad? No. Each kid only gets 1 allele from each parent. So if she got the capital B from dad, the only thing that she could get from mom is a lowercase b. So she gets brown from dad, blonde from mom, and because brown is dominant, she ends up with brown hair. Now, the kid here has brown hair. Their other kid has blonde hair. So if she has blonde hair, she got a lowercase recessive allele from both of her parents. So one of these had to come from dad, and one of these had to come from mom. So she's got 2 lowercase b's. They are both heterozygous. Now this kid right here, she has brown hair. We know she's got a dominant allele. But who'd she get it from? She get it from dad? She could have got it from dad. She get it from mom? She could have got it from mom. We don't know who it came from, so we can't tell what the second allele is going to be. So unless she has kids and she ends up having a kid with blonde hair, we can't say for sure if she has two capital V's or capital and a lowercase. So what we're looking at here are called autosomal pedigrees. That means that they're traits that are on the autosomal chromosomes. So those first 22 pairs, the first, if you have 46, so that'd be the first 44 chromosomes. Those last two, they have different inheritance patterns. We'll get more into that later. But if you see traits that don't skip generations, it's probably dominant. If you see traits that do skip generations, where you have parents don't have it, but the kid does, it's recessive. That's kind of the usually how to look for if you're trying to figure out is it dominant or recessive. In the cases of what we're looking at right now, most of them that we're going to talk about are just normal autosomal recessive traits. So on a scrap paper, draw a pedigree with your parents, and if you have any, do the siblings. Okay, fill in the circles and squares for whoever's right-handed. So just practice, make a pedigree with those four, with whoever, with dad, mom, and you and your siblings if you have them. Just for practice, if you can. If not, don't worry about it. We're just going to move on. If you want to do that, go ahead and pause and catch back up later. So first example here, it's kind of a doozy. We're going to make a pedigree for left-handedness using the information of the Thomas family. So the father, Tom, mother, Diane, have 3 children. So I know I've got mom, dad, and then 3 children. The 2 oldest are Anna and Mary, so girls, they'd be circles, and the youngest is Teddy. He'd be a square. Now, it doesn't matter the order left to right of which kids you do. Normally, it's oldest on the left, youngest on the right, but it doesn't matter. The oldest daughter, Anna, is married and has an older son, Will. So you got to give her a marriage square connection and then a square for her son and a circle for her daughter. Mary is also married and has a son, Patrick. Teddy, the son, is not yet married. Everyone in the family is right-handed except the father, the oldest daughter, and the granddaughter. And they're telling us that right-handedness is dominant. So we've got Tom and Diane, who are married. They have 3 kids, Anna, Mary, and Teddy. Anna is married with 2 kids, Will and Vanessa. Mary is married with 1 kid, Patrick, and Teddy is not married. Now, right-handedness is dominant, so we're going to shade in everybody who is right-handed. And it says everyone in the family is right-handed except the father, Tom here, the oldest daughter, I think that was Anna, and the granddaughter, Vanessa. So they're all left-handed. Everybody else is right-handed. We're tracing the right-handedness. So we filled all those in. Now, if right-handedness is dominant, 2 dominant alleles would be right-handed. Dominant recessive heterozygous would be right-handed, and homozygous recessive would be left-handed. So the first thing we'll do is fill in everybody who's left-handed. We know that they can only be homozygous recessive. So 2 lowercase r's, 2 lowercase r's, and 2 lowercase r's. Next step. We're going to fill in every dominant allele with at least one, or dominant, everybody who has right-handed, they have at least one dominant allele. So they're all getting capital R, capital R, capital R, capital R, capital R. We know for sure they're right-handed, so they have at least one. Now, do they have 2? Are they homozygous dominant or heterozygous? Well, we have to look at other people to figure it out. And the key here is mostly going to be these left-handed people. So, based on the parents or offspring, we're going to infer what the other allele for the dominant phenotype is. So, for example, these 2 right here, if the child is homozygous recessive, okay, This one right here is homozygous recessive. He's left-handed. Then it had to receive one allele from each parent. Had to get a lowercase r from him. No big deal because he is left-handed. But she's right-handed. So to have the left-handed kid, she also had to have a left-hand gene to give to the kid. Only heterozygous or homozygous recessive parents can produce homozygous recessive offspring. You have to have a recessive allele to have a kid with a recessive trait. These parents are right-handed and therefore not homozygous recessive. Okay, so this parent here is heterozygous to give the lowercase r to this kid, and because this kid has left-handed, got a lowercase r from her and a lowercase r from him. Now, if a child has one dominant allele, all right, now the rest of these people. So if this kid here, this one right here, this one right here, this one right here, they all had a parent who is homozygous recessive. Okay, so they got their capital R from who? He got his capital R from dad. Okay, he's the only one with a capital R between the two, so that's what he got from him. Now, he didn't give both alleles to his kid. He gets one from each, so the other allele had to come from mom, and the only thing she can give is lowercase r. Same with these. So they all got their capital R from who? They all got it from mom. Now, the other allele had to come from dad. The only thing he could give is a lowercase recessive r. So they're all heterozygous. Now, this kid here, I believe it's Patrick. So Patrick got a capital R from who? Could be mom or dad. So what's the second allele? We don't know. Now, sex-linked pedigrees are going to deal with sex-linked traits. Now, we'll get more into that a little later once we go back over karyotypes and chromosomes a little bit. So they're traits that aren't on those first 22 pairs. They're on the last chromosomes, those X or Y chromosomes. Now, males only have one X chromosome and are likely to be affected by an X-linked trait. So if it's on the X chromosome, they only have the one, so they can't be heterozygous, they can't be carriers. They either have it or they don't. So if you see a pedigree with pretty much just males being shaded in, it's probably what you're looking at. We'll get more into that later. Now, there is a Amoeba Sisters video which goes over pedigrees that's very helpful. They go into sex-linked traits too. You don't have to watch that just yet. There's the handout right here that helps go along with that if you would like to use that. There's a few more practice questions with some pedigrees. Some are easier and some are harder. This is some more practice, and the link can take you to the full worksheet that has the questions on it. This is just another example of a pedigree. This one's actually a sex-linked pedigree. We can see here that pretty much the only ones that are fully shaded are males. So it is a sex-linked trait. And this is specifically hemophilia in the lineage of Queen Victoria. So this is a real pedigree. We see halves filled in circles here, and this is a way of showing a carrier. So like someone who's heterozygous for something. Now, you don't always shade in the carrier, but sometimes you do. And I hope that was helpful.